Hey everybody, welcome back to our video series here. We've been talking a lot about phases of matter and what's going on with these particles. We talked about changes in those phases, and the changes in those phases had something to do with the temperature, and how fast things are moving around, how much kinetic energy they have. Temperature obviously is the measure of the kinetic energy, the average kinetic energy of a group of particles in a substance. And when we're looking at that, if we were looking at something that was heated up, and the particles would be moving much more rapidly than if we were looking at something wherein the particles were cooled down. They'd be moving much more slowly. Obviously, if we can get enough motion going, we could turn a solid into a liquid, even if it were iron, like a horseshoe might be made out of, or steel, or something along those lines. You could add enough heat to actually turn something that's normally solid at room temperature into a liquid or even a gas. So temperature is obviously this average motion going on, this average kinetic energy of a group of atoms, ions, and molecules. We measure it with a thermometer, okay? And we have a couple of different systems for that. We got Kelvin, we have Celsius, we have Fahrenheit. You're really used to Fahrenheit, most likely. Uh, a lot of times, it's pretty rare to meet someone at our grade level who is thinking in terms of like Celsius. It's funny because as you work with these, especially if you went into a career in science or engineering, you might find yourself thinking more in terms of Celsius. Um, Now, Celsius and Kelvin, Kelvin's probably new to you. They're actually the same as far as like uh, the degree or the magnitude of the size of one unit. So 1 degree Celsius is 1 degree Kelvin. The difference really is where they start. So Kelvin says, hey, let's make zero be absolute zero. So absolute zero, remember, there is nothing moving at absolute zero. Okay. While Celsius, you actually have zero being where water freezes. So for Celsius, zero is where water freezes, 100 is where water boils, and it goes up in even steps from there. Um, so Kelvin obviously would be 273.15 Kelvin units lower than where Celsius starts. That's where absolute zero happens to be. A Fahrenheit unit is about 1.8 of a Celsius degree. So for every 1 or 2 Fahrenheits, you have about 1 Celsius or so. It's not exactly perfect. The conversion factors are right there for you at the bottom, from Fahrenheit to Celsius and Celsius to Fahrenheit. So thermal energy is the amount of energy inside uh, a system of particles. So if you have a large system at a certain temperature, okay? So if I'm at a certain temperature, my particles are in motion, right? So let's say I got this system and it's at 25 degrees Celsius, right? But it's just a bottle of water. Well, if I have a pool of water that's at that same temperature, there's so much more mass in that temperature that there has to in that system that there has to be a ton more motion going on within it. There has to be a ton more thermal energy contained within that larger body than would be in the smaller bottle. Okay. So thermal energy is dependent both upon the temperature of an object as well as the size of an object. This is a common question that will come up, being asked if, um, half a liter of water at 20 degrees Celsius, has more or less thermal energy than 5 liters of water at 20 degrees Celsius. And the one with more mass always wins as far as thermal energy goes, as long as the temperature is kept constant. So then, what is heat really? Heat is the flow of energy from one object to another, and heat always flows from a warmer object to a cooler object. So if you picked up a hot mug of hot chocolate, you would feel that heat transferring into your hand. Whereas if you were holding an ice cube, the heat from your hand is going to transfer into the ice cube and melt it. And that kind of goes back into that whole exothermic, endothermic kind of concepts that we were talking about previously. Every material has a different capacity for this. The specific heat is the amount of energy required to raise the temperature of a kilogram of a substance by 1 degree Kelvin or Celsius. Okay. Now, if you notice at the top of this list is water, and that's actually really super important. Water is very, very good at uh, taking in heat. It takes 4,186 joules, which is a unit of energy, to heat up a kilogram of water by a degree Celsius. So there's a lot of more energy required than a lot of other objects. If you look at, say, soil, typical soil takes 1,046 joules to raise the same amount of temperature in a kilogram of the substance. So a kilogram of soil needs about a fourth of the energy of a kilogram of water to raise its temperature. And that's really important, especially for the oceans. Keep in mind that the oceans cover a huge amount of the Earth, and they're going to absorb the energy coming in from the sun a lot better than the soil does. So, how does heat transfer? There's 3 main ways, and these 3 main ways are actually playing a role in the entire world around us. So radiation, conduction, and convection are the 3 main ways that heat is transferred. The radiation coming down from the sun would heat the ground would heat the air, and the air would rise up through convection. Conduction is the transfer of thermal energy when there's no transfer of matter. So let's say you were heating up a metal rod. The metal rod's getting super hot at that one end. You can see that the metal rod's white hot at one end. But as you come away from that furnace, the color of the rod changes. However, the heat is going to transfer from the super hot white hot end all the way down to the cooler end that's on the other side of the rod. So conduction doesn't move the matter. It's moving the energy from one end to another. And you see that all the time. If you pick up a hot pan off the stove, chances are the handle is hot, especially if you're using something like a cast iron skillet like I do. So the cast iron skillet easily transfers heat all around, and you feel the conduction of heat into the handle from the heating element of the stove. Convection, on the other hand, is a transfer of energy when the particles of a liquid or gas move from one place to another. These motions are generally circular, and they move from hot to cold. So you can see that the cool air coming off the sea hits the hot land, warms up, grows less dense, goes up into the sky, but then starts to cool down and sink and lands back onto the ocean, and it just keeps moving around the hot and cold areas. The same thing's going on at the core of the planet as well. So if you go back to the lava that we were looking at from Hawaii last time, the same sorts of concepts of convection moving from hot to cold is always going on all throughout the planet all the time. And finally, we have radiation. Radiation, all objects actually radiate energy. Okay, that's pretty key. We obviously think of the sun as being one of the largest objects that's radiating energy out all the time, right? The transfer of thermal energy by waves moving through space. Now, we're going to talk a lot about waves this year. Um, and radiation is our first little taste of that, that there is energy being transferred and moving through space from objects radiating it off. That's really about it for today. Ultimately, there's a lot of vocabulary happening. You're going to want to get on top of that. Make sure that your notes are containing some of these new keywords, um, thermal energy, that kind of stuff. It's very important to understand that mass and temperature combine together to find the total thermal energy in a substance or in a object. That's extremely important as a concept, and we're actually going to be digging into those equations later on when we start building hot and cold packs and looking at how different salts can heat up water differently. That's pretty much it for right now, though. So make sure you check Quizlet for some of these vocabulary terms and make sure that your notes have captured some of this stuff so that you can start learning them and incorporating them. And otherwise, have a great night, guys. Bye.